Hi, I'm Mark Barsamian. In this video, I'll be discussing basic derivative properties, the constant function rule and the power rule. This material is from the book section 2.5, Basic Differentiation Properties. And more specifically, it's from the middle of page 145 to the middle of page 148, examples 1, 2, and 3. The corresponding homework is constant function rule and power rule problems from section 2.5, these 6 problems. Today we'll learn our first derivative rules, but before embarking on that, it'll be useful to review 2 things. One is the concept from the prerequisite material, power functions. The other concept is just from the last 2 videos, the definition of the derivative and the 4-step process. First, our review of power functions. Recall that a power function is a function of the form f of x equals x to the k, where k is a real number. Now, power functions can be presented in various forms, and it's useful to have names for the forms when you're working with them. The power function form is this basic form. So k can be a positive or negative number or 0. So, for example, all of these things are power functions in power function form. X to the 7th, x to the 1, x to the 0, x to the minus 5. Now, people are often confused by expressions with negative exponents. Because of that, it's often a good idea to present functions in a form that has only positive exponents. We'll say that a power function is in positive exponent form if all of its exponents are positive. The rule of exponents that says x to the minus k is 1 over x to the k will allow us to convert between power function form and positive exponent form. So, for instance, x to the minus 5 is the same as 1 over x to the 5. So on the left, we have an expression in power function form, and on the right, we have an expression in positive exponent form. Same function, just different presentations. Most students are comfortable with the square root function, f of x equals square root of x, but power functions that are presented in more complicated radical form, such as this, g of x equals the 5th root of x cubed, can lead to confusion. Furthermore, it's not really possible to do much arithmetic with power functions that are in radical form. You first have to convert them to power function form. To do this, you have to recall the definition of what the radical form means. The nth root of x to the m means x raised to the m over n power. Rational exponent form is just what it sounds like, a power function with an exponent that's expressed as a rational number. So, for instance, here are 2 power functions that are expressed in rational exponent form, x to the minus 7/3 and 1 over x to the 2/5. Let's go back up to our previous equation. In this expression, we have a power function expressed in radical form, and on the right side, we have the same power function expressed in rational exponent form. I want to discuss briefly working with rational exponents. 2 important basic facts are useful when you are dealing with power functions that have rational exponents. The first basic fact is just the commutative law of multiplication, that you can change the order of multiplication. So the fraction m over n can be thought of as m times 1 over n. It can also be thought of as 1 over n times m. A second useful basic fact is just this rule of exponents, what it means to have a raised to a product, b times c. A raised to the b times c is equal to a raised to the b, and then that result raised to the c power. These 2 facts can be combined to tell us how to work with rational exponents. For instance, we can do this. X raised to the power m over n is equal to x raised to the power m times the quantity 1 over n. But that's also equal to x raised to the m, and then that whole result raised to the 1 over n power. But we can also do this. Notice that in these exponents, I have an m on the left and a 1 over n on the right, But the commutative property tells me that I can multiply those numbers in either order, so I could write the exponent this way with the 1 over n on the left and the m on the right. So I just change the order of multiplication in the exponents. That's the commutative property of multiplication. But if I think of the power function that way, then this is telling me to start by doing x to the 1 over n power and then raise that to the mth power. That may sound very finicky, but it can make calculations much easier if you pay attention to which form is more helpful. So for instance, suppose you have to compute 8 to the 2/3 power. Well, you could do that by doing 8 squared raised to the 1/3 power, so you'd have to do 64 to the 1/3 power. You'd have to remember that the cube root of 64 is 4. Or you could do this. 8 to the 2/3 is equal to 8 to the 1/3 squared. So you just have to remember that the cube root of 8 is the number 2. So that's easier, I think. Remembering that the cube root of 8 is 2 is easier than remembering that the cube root of 64 is 4. Now, I want to discuss briefly the definition of the derivative and the four-step process from the last couple of videos. Remember that the symbol f prime of x is spoken the derivative of f of x, and it means this, the function you get when you do this limit. And we have, in the last couple of videos, been using the four-step process for finding f prime. It's this difficult process, messy, and takes a long time, but that's how we have found f prime of x. So when you use the definition of the derivative, it means that you're building this limit expression, which is what the definition of the derivative says, and it's hard and it takes a lot of time. So in the current section, we will not use the definition of the derivative. We'll use what are called derivative rules. These are just certain forms of derivatives that occur frequently and for which a certain pattern in the result can be observed and put into the form of a rule. Before learning some derivative rules, we need to learn about some new notation for the derivative. So we have a new symbol, this symbol. It's spoken df of x dx. And there's another symbol that's new, this one. It's spoken d over dx of f of x. It's also spoken d dx of f of x. They both mean the same thing. They just mean the derivative of the function f of x. So in other words, they just mean the same thing as this old symbol. And there's another new symbol, this one, spoken dy dx, or you could say dy over dx. When you use this symbol, the letter y represents a function of x that's been introduced by some equation. That is, in function notation, you would say that you have a function y parentheses x. Now, what this symbol means is the derivative of the function y of x. In other words, it would mean y prime of x. So in this video and throughout the book, you'll see all of this notation used. Now, this new symbol, df of x dx, might look kind of random to you, but there's a certain reason for it, why it looks that way. Remember that the definition of the derivative is this thing. This expression involves the limit of a difference quotient. The thing inside this limit is a difference quotient, and that difference quotient computes the slope of a secant line that touches the graph of f of x at 2 points. That is, it's the change in y over change in x formula that gets you this expression. Now, in this symbol here, that triangle is actually the capital Greek letter delta, and it denotes the change in a quantity. The h that's in the denominator denotes the change in x, delta x. And so when you find the limit as h approaches 0, that could be thought of as the limit as delta x goes to 0. So this derivative expression here could be thought of this way. F prime of x is the limit as delta x goes to 0 of delta y over delta x. Or you could think of it this way. F prime of x is the limit as delta x goes to 0 of delta f of x over delta x. So our new derivative symbol, df of x dx, with its small letter d, is meant to signify that it's a result of a limit of this symbol delta f of x over delta x, which has its capital letter delta. In other words, little df of x over little dx is equal to the limit as delta x goes to 0 of delta f of x over delta x. So the little d's are supposed to remind us that the derivative df of x dx is obtained by doing a limit of delta f of x over delta x. Finally, we get to the derivative rules. So we'll discuss two today. The first one is called the constant function rule. The constant function rule is used for finding the derivative of a constant function. I'm going to present it in two forms. If f of x equals c, then f prime of x equals 0. So if your function is a constant function, then the derivative of your function is 0. You can express this in single equation form this way. d over dx of c equals 0. So let's do an example. Let's let f of x equal 7 and find f prime of x. Well, let's use the two equation form. Using the two equation form, we just write down that f prime of x equals 0. Now let's use the single equation form. So there is the single equation form. Notice that on the left I have d over dx of 7. On the right, I don't have a d over dx symbol. I just have the number 0. So this whole symbol stands for the result of finding the derivative of 7, and the result is the number 0. Question B is, using a graph, discuss why the result makes sense. Well, let's make a graph of f of x equals 7. So a graph of f of x equals 7 is just a horizontal line with y equals 7. Let's think about the tangent lines on that graph. All the tangent lines on that graph are horizontal, so their slopes are all 0. Now, what does that mean then when we want to think about the graph of f prime of x? Remember that the number that is the slope of a tangent line on the graph is the same as the number that's the value of the derivative. So at each of those x values where there was a horizontal tangent line on the graph of f of x, there's a point on the graph of f prime of x that has y equals 0. So the points on the original graph have y value of 7, but the tangent lines have a slope of 0. Well, the numbers that are the tangent line slopes become the y values on the graph of f prime. So the graph of f prime is going to be this line. That's why it makes sense that f prime of x is 0. The second derivative rule that we'll discuss today is the power rule. Remember, a power function is a function of this form, f of x equals x to the k, where k is a real number. So the power rule is used for finding the derivative of a power function. We have a two equation form. If f of x equals x to the n, then f prime of x equals n times x to the n minus 1. And we have a single equation form that says d over dx of x to the n is equal to n times x to the n minus 1. Now note that in both presentations of the power rule, the original power function, that is before finding the derivative, the original power function is in the form x to the n. That is, the original function is in power function form. So for our next example, we'll let f of x be x to the 7th, and we'll find f prime of x. Let's use the two-equation form of the power rule. So we start by writing down our original function, and we identify clearly what the power is. And we give it a name, n. And then we build this expression using the value of n equals 7. Notice that I don't do the arithmetic in the first step. I just write down what the power rule says. The power rule says we're going to do n times x to the n minus 1. It's in the next step that I simplify that. That may sound needlessly finicky, but it's a bit of basic arithmetic that it's going to be important in some problems to separate your steps into small, simple steps so that the arithmetic is as simple as possible. Now let's do the same thing using the single equation form of the power rule. Using the single equation form, the answer comes out to be the same. It just all happens on one big equation. Notice the format. I don't do anything to that original expression. I don't do any arithmetic on that expression. That's the left side of the power rule. And this is the right side of the power rule. On the left side of the power rule, there is a d over dx. On the right side of the power rule, there is no d over dx, and there is this arithmetic going on with the exponent. So the arithmetic happens on the right side of the power rule. The d over dx happens on the left side of the power rule. For our next example, find dy dx for y equals 1 over x to the 7th. Notice that this is a different style of question. The derivative symbol is in a slightly different form than in the previous example, and the function is presented in a slightly different form. It doesn't say f of x, it just says y equals. The function is presented in an equation. Well, the key solution is that we have to rewrite our function in power function form. So our function in power function form is x to the minus 7. So now find the derivative. So notice the same approach. We write down our original function with the d over dx next to it. We identify clearly what the exponent is, what the power is. And so the left side of the power rule has a d over dx in it. The right side of the power rule does not have a d over dx in it, but it has this arithmetic in it. Now, when we do the arithmetic, notice that we get a result that has a negative exponent. So this is power function form here, but it's, I think, clearer to convert to positive exponent form. So remember that our original function was in positive exponent form. So it was useful, we had to rewrite the function in power function form to take the derivative. Once we find the derivative, though, it's clearer to convert the result to positive exponent form. Notice one more thing. The previous problem, we found that the derivative of x to the 7th was 7x to the 6th. In the current problem, we found the derivative of 1 over x to the 7th. Notice that the result is not 1 over 7x to the 6th. It's not 1 over the derivative of x to the 7th. The result is very different. It's negative 7 over x to the 8th. Example 4. Let f of x be x to the 1/3. Find f prime of x. And then in part B, find f of 8 and f prime of 8. So there's the same form we had before. We write down the left side of the power rule, which has the d over dx on it, and does not have any arithmetic going on. And then we write down the right side of the power rule. Notice the right side does not have the d over dx symbol, but it does have this arithmetic going on. And then notice that once we get that form, we do 3 steps of rewriting. We end up with something in positive exponent form. So our result was in power function form, which is a nice form, but it happened to have a negative exponent, so we rewrote it. Now for question B, we're supposed to find f of 8 and f prime of 8. So the cubed root of 8 is 2. So f of 8 is the number 2, f prime of 8 is the number 1/12. So here we used our facts about exponents and fractional exponents to rewrite the result. So a lot of you might think that something like 3 times the quantity 8 to the 2/3 is something you would need a calculator to find the value of. But in fact, we can do this using basic arithmetic. All right, example 5. Find d over dx of square root of x. We have to start by rewriting the function in power function form. Then take the derivative. All right, so notice again the format of the solution. We have the left side of the power rule, which has the d over dx and does not have any arithmetic going on. And then we have the right side of the power rule. And notice that we have 4 steps of simplifying the answer, putting the result in a more common form. Now we have to be careful when you write a fraction that the horizontal bar is very clear. In this expression, I want to make clear that the 2 and the square root of x are both in the denominator. Example 6, find dy dx for this function. So we have to start by writing the function in power function form. Then you find the derivative. So notice the format, left side of the power rule, which has a d over dx and does not have any arithmetic going on. The right side of the power rule, which does not have the d over dx and has some arithmetic going on. And then notice 3 steps of rewriting the result. So we ended up with a result that was in power function form, but it happened to have a negative exponent. So we rewrote it in positive exponent form. On to the next example. Find the derivative of f of x equals x. Well, let's start by rewriting the function in power function form. Now find the derivative. So the same format, left side of the power rule, which has a d over dx and does not have any arithmetic, followed by the right side of the power rule, which does not have the d over dx and has some arithmetic going on. And then we have 3 steps of rewriting. That's question A. Question B is, using a graph, discuss why the result makes sense. Well, let's make a graph of our function f of x. Well, the graph of f of x equals x is just a straight line, which has equation y equals x. Now think about the tangent lines on this graph. All of these tangent lines have slope m equals 1. All of the tangent lines on the graph of f of x have slope m equals 1. And that fact tells us that all of the points on the graph of f prime of x have y value of 1. Because remember, the value of the derivative is equal to the number that's the slope of the graph of f of x. So at each of those x values where the original graph has a tangent line that has a slope of m equals 1, correspond to, on the graph of f prime of x, at those same x values, the y value of f prime of x is 1. So that means that the graph of f prime of x is going to be a line with equation y equals 1. That's why when f of x equals x, f prime of x equals 1. So that's using a graph to discuss why our result makes sense. Our last example, when y is equal to 1, find y prime. We rewrite the function as a power function, and it is the function x to the 0. So we use the power rule to find f prime. So d over dx of x to the 0. We get that the derivative is the number 0. Now in question B, I want to change the question. I want to compare the result from example 8 to the result from using the constant function rule. Y is equal to 1. So using the constant function rule, we would find that the derivative is 0. Same result. That's the end of the example, and that's the end of the video. Thank you.